Thanks a lot for inviting me, and thanks everyone for making it today. So today we have divided our talk into radio and X-rays, and I'll try to motivate why do we need these wavelengths. I will be covering broader cosmology, which is my primary field of interest, and what makes us design these kinds of very weird looking systems that you are looking here. So with that, I'll get started. And yeah, please feel free to ask questions anytime. Of course, we'll be open to questions at the end too. So the very first thing where I think astronomy differs very significantly from major disciplines is the length scales involved in our problems. And it's a sheer range from kilometers to megaparsecs. And our brains are mostly incomprehensible to basically imagine these kinds of scales. And so in this talk, I will mostly be talking about what we call as the large scale structure. So for the public here, I just want to motivate it with this slide. And these are the kind of objects that we are familiar with. We have a human right there to just set the scales right. And we can basically now move the scroll and see what kind of length scales we keep on uncovering as we move towards the right of the spectrum. Right. So this is basically the kind of minimum. We are talking about 10 raised to 3 to 10 raised to 4, so roughly a kilometer. And we start uncovering these asteroids and some of the planetary satellites, and then we can move further. We can go to some thousands of kilometers, and suddenly we start seeing our more familiar solar system objects like Earth and some of the stars. But this does not end here, especially for cosmology that I'll be talking about. So we'll move further. And we are already now talking to scales which are slightly incomprehensible. We are talking about 10 raised to 10 meters, which is basically a meter followed by 10 zeros. And here we are still looking at few compact objects, something that maybe our colleagues will discuss later. And I'll fast forward this to then get to the relevant scales that we are interested in, which is parsecs and light years. And just a definition is, it's the amount of time light takes to travel. Light year basically is the distance it travels in 1 year, and parsecs is roughly 3 times that. So that is the kind of length scales where cosmology gets to be very interesting. Because in cosmology, what we are looking at is large scale structure of the universe, and I'll get on to that later. But we'll keep moving. This is yet not the end. So we'll continue. And now we are not looking at specific stars, but we are starting to look at cluster of stars or even galaxies, like we live in Milky Way galaxy. So we are already at that kind of a length scales. So it's not 1 light year, so which is basically light does not take 1 year, but it can take tens of thousands of years to travel across these galaxies. And these are the length scales that I'll be talking about today. And of course, one can move even more and go to something called megaparsecs. And these are the length scales where it's not just galaxies, it's millions of galaxies together. And this is where we start to see how universe is actually structured, right? So this is where I'll start my talk with. So as a cosmologist, what do we study? The very first thing is, what is it that our universe is made of, right? So we do see human beings, we see metals, we see non-metals, but as some of us know, that's a very small fraction of what the universe is really composed of. Most of the matter in the universe is not visible to eyes, or for that matter, any of the telescopes. And that's basically our dark matter and dark energy. They could be individually, each could be like a seminar. But it's interesting to understand the composition of this universe. And of course, the moment we start to look at the composition, the question are, what are these things that we are unable to see, and they comprise the maximum energy of the universe? And to be honest, we don't know much. And I'll stop there because, again, I can take up questions later if required. How is the matter distributed? So, okay, we have come to terms with the fact that what we see is just a 4% thing. But this 4%, how is it distributed? And that is something I'll come to later. A lot of people research on why do we just have matter, right? Because initially, when we talk about the evolution of the universe, there is equal likelihood of having matter and antimatter. So there is that. But mostly today, I'm going to focus on the last part, which is given some initial conditions, some way the universe started, how did it evolve to what we see around, right? So probably in Bangalore is not the best place, but if you go slightly outskirts, you will see a sky studded with stars. And from some Big Bang or something that I'll come to later, how did we get here? And what are the crucial periods that we want to study here? And the beauty of cosmology lies here. Unlike traditional history, where if you have to study the past, you have to look at inscriptions, you have to look at your primary sources, secondary sources, and try to interpret things. In cosmology, we can directly see the past. And that's what makes it a more interesting discipline and probably less speculatory. And the reason for that is very simple. Light takes a very finite time to travel to us. So we are looking at sun, and the light takes roughly 8 minutes from sun to reach us, which means that we are already starting to see the past, right? Sun, what we are seeing is 8-minute-olds, and you can just stretch this. You can stretch it all the way to all the length scales that we talked about, light years, thousands of light years, even mega light years. So when we see those things, we see them as millions of years back, right? So we can actually build telescopes and see the past. And this is where I'll focus on. So the evolution of the universe itself, as we understand today, comes with a very tiny perturbations. And I'll just play a video to highlight that. So what we understand is we had very tiny blips in the densities all over the place. And what you are seeing is a time lapse in units of billion years, which is the typical cosmology time scale that we talk about. And slowly what you start to see is these high density points get seeded with these stars and galaxies, and they start to emit light, right? So as we approach a few billion years, suddenly there is illumination. This is something what we call as cosmic dawn, something that I'll elaborate in much detail later. And then this continues. Of course, all these stars have very limited time. So at some point, you will start to see tiny explosions, right? So one of the very massive stars, when they die, they explode, and they enrich their environment with lots of metals, which in turn then helps to form more stars. So it's like a nice feedback process that leads to a lot of structures. And this is what we see in the night sky today, right? So this continues this kind of process, but the idea is that if you could just take a step back and look at the universe as it is, you would see that these are arranged in a very specific pattern. These are called filaments. And these are the regions where the density of the universe is slightly high, and therefore you will see the stars being there. So coming back to my presentation here, the question is, how did it all happen? So this is like a summary of all I have been talking about till today. We start with something called Big Bang, and this is basically one of the possibilities, probably the most accepted possibility, because it does explain a lot of things we see around us. Very close to the Big Bang, we had a period where universe expanded exponentially, something we call inflations. And roughly around this time, we are talking about already a few 100,000 years after the Big Bang, that we had these first light coming to us when the first atoms in the universe formed. And we can still see it. As a matter of fact, this was awarded Nobel Prize in 1965. When we first detected this relic of the Big Bang called cosmic microwave background. And our field of study starts right there. So since the 60s, this part of the universe has been studied in a lot of detail thanks to different experiments around the globe. So we kind of understand how universe was in its very infancy, when it was almost 1 year old or less. And fast forward to today, as an adult universe, we can see all around us with state-of-the-art telescopes and basically see how the structures are distributed. But there is a gap here, and this gap is when the very first stars formed, right? Because we see stars today finally implies that they must have started somewhere, and this is what we call as cosmic dawn. That is something we don't understand, because in some way you need stars to form stars. So it's a chicken and egg problem leading up to the question, how did it first start? So in some way, you know the universe as an infant, you know the universe as an adult, and you are asking the question of how it was as a teenager. And it's not a very linear process, right? You can't just interpret just by looking as an adult of how they were. It's exactly the same with the universe. So then you have to go out and build things that can directly see these parts of the universe. And that's precisely what we do. And just to give a rough time scaling picture, of course, what we are showing here is a very linear looking picture, but it's actually not. And one of the very nice way to interpret this is you imagine this entire thing from the Big Bang to today happened in 1 year of time. Just compress everything. And if you do that, we are basically studying January of the universe, which is where the Big Bang happened, which is where the first atoms formed, and this is where the first stars formed, right? And just to look at this perspective, we are somewhere here. The final month of this 12-month cycle. So we are really probing the very past of the universe, roughly just a few fraction of the total age of the universe. And of course, all the scientific revolutions that we are seeing is the final second. So in cosmic timescales, this is almost negligible. Okay, so the questions that we are asking is, okay, we had something right here, the first atoms have already formed in the universe, but there are no stars and galaxies, right? So it's all just hydrogen gas at this point. Universe, the most abundant element is hydrogen. At some point, you do have these stars forming. Somehow, we still don't understand that. But what they do is stars radiate. We see that in the night sky. And they begin to transform the universe, right? Because stars, of course, affect their neighborhood, which in turn affects more things. And finally, over a few 100 million years, you begin to see the entire structure of the universe transform because of this. So the question that we are asking is, what is the nature of these stars? The very first stars in the universe, are they exactly the same as what we see today? Or is there a difference? And of course, there has to be a difference. When did they actually form? Of course, I said January, but the exact timescales are completely unknown here. And how exactly they impacted their surroundings. Of course, we have a lot of models, but very little data to basically distinguish between what is correct and what's not. And these are the key questions that we are asking with our research. And how do we see it? So as an astronomer, when you look at a period, okay, this seems exciting to me. The first question that we ask is, how do I observe this and verify this? And the source that we have chosen is nothing but our hydrogen atom itself, given that it is the most abundant element in the universe. So hydrogen atom is the simplest atom. You have a proton and you have an electron. They have something called spins. And if there is any process that can change the spin of electron, there is a specific signal which is released at a very specific frequency. And this frequency is 1420 megahertz. And I'll come back to why this is important. But the idea is, if we had to design a radio, this is in radio frequencies, if we had to design a radio and tune our radio to that frequency, we should be able to see the hydrogen around us. And that is exactly what's been done for different galaxies. So this is one of the pictures of our nearby galaxy. This is typically how it will look when, say, a Hubble telescope sees it, or one of these JWST or powerful telescopes see it. But the same picture, if you could see at these frequencies, basically you start to see the hydrogen gas, you will get something like this, right? So this brings me to the very next part, which is our universe is intrinsically multi-wavelength. Our eyes, we only see a very small part of the spectrum, which is visible spectrum. They tell very little to what's going on. And in order to understand everything, we really have to look in other wavelengths, right? So this is, I think, analogy we all understand, which is this blind man probing the elephant and deducing different things. And it nicely says our own experience is rarely the whole truth. As philosophical as it gets, this is also true for astronomy, which is if you look at a very specific wavelength and probe the universe, what you will really deduce will be one of these. And therefore, you really have to bring everything together and then lay out the whole picture. And just to give you a glimpse of how that is, let's look at our own galaxy. So if you go to a really pristine region and look at the Milky Way, you will see something like this. Very beautiful, great experience to witness this. But again, as I said, this is visible. This is something our eyes can see. But we can also go in different wavelengths, and you can see how dramatically this changes. If we could just change our wavelength to X-rays, which is one of our next talks, you will see a completely different picture. I can also tune to infrared. I could tune to our favorite hydrogen signals. And you can see how dramatically these structures are changing. And they are telling us a lot of different things, some of which will be covered in the next talk. But the idea is that you really need all of this information to understand the entire processes that are happening here. Right? All right. So this is just a summary of our Milky Way. And because we are primarily interested in this specific signal from hydrogen, we are mostly looking at the faintest part, which is megahertz frequencies. And I'm sure everyone in this room is familiar with these frequencies because of our radios operate here, right? So 100 megahertz, 98.3, 95, these numbers are all those frequencies where we can see our universe. And it's not one size fits all. So if you want to see these wavelengths, you have to build very different kinds of instruments. Again, some of it will be discussed later, and some of it will be discussed just now. Actually, these instruments are right in front of you, and I'll describe them a bit. Right? So focusing on what we see, we observe universe not in the visible, but in radio wavelengths. And our understanding is that we want to detect this faint signal that's coming from the first stars in the universe, which we can very clearly see in radio, not so clearly in the visible light, unfortunately. So we can't really see them, but we can kind of see them by building telescopes. And this field itself is fairly recent compared to astronomy. Astronomy is millennia old. People have been stargazing since the humanity started. But this is roughly 1930s. So we have Carl Jansky here, who was designing a system for communication, because of course these frequencies are what we use for mobile phones these days, Bluetooth, FM radio and whatnot. So he was doing a similar thing. And he started to see some unexplained signal, which was not aliens. So he started to see that, and he started to see that it repeats. It repeats every 24 hours. And eventually it led to the conclusion that universe is sending us something which is in the radio wavelengths. And Groth Reber here got very excited about this prospect, and he literally built this entire telescope in his backyard all by himself. And he started observing the universe at these frequencies. So this is in some way the birth of observing this in radio, what we call as radio astronomy these days. So we do very similar thing, but of course with a lot more accuracy, which is we design these kinds of very differently looking radio telescopes and let it observe the sky signals and then try to deduce what can we say about the first stars from the data that we collect. So of course, the data that we collect is not pristine at all. Okay? So as a experimentalist, I will design a receiver, for example, FM, right? We all have FM in our phones. At 100 megahertz, I want to see the signals from the first stars, but I will probably listen to Akashvani. And that's a major, major contamination to what we can do with astronomy. So the very first thing that you will see in your data is terrestrial, human beings, electronic devices, all kinds of transmitters, and Girish in the next talk will talk more about it. And Units really don't matter, but do pay attention to the numbers here. So in whatever units we are measuring the power, this is roughly 20,000 or so. Suppose we could somehow get rid of this. The moment we get rid of this, we will start to see this beautiful galaxy. Just like what we saw in visible, we could also see this in radio. And it's, I would argue, more exciting. Nevertheless, it's still a contamination, because what we want to see is beyond our galaxy. What we want to see is the first stars. And therefore, this is a problem. This is yet another thing that we have to deal with, what we call as foregrounds, which in turn is very interesting to understand the processes that are happening in our Milky Way galaxy, but a nuisance for cosmology. And again, the units, it has of course reduced from 20,000, we have gone to 2,000, but still not there yet. Suppose magically I could subtract it out completely with whatever magic. I will still not go to the signal. There is something at 10 or so, which is my telescopes that are here, they are not ideal. They do have their own contaminations added. And that's exactly what you will see after you have taken care of these things. Finally, if somehow I could also get rid of these things, I will finally get down to the signal that I'm looking for and look at the units here. So we are looking at 0.02. So just to recap, we basically take this system here, put it out in one of the pristine locations, we start collecting the data, and we of course start to see the interference. We somehow fix it, we get back to our galaxy, we somehow fix it, we get to our own contaminations from our telescopes. And finally, if we are very meticulous and very accurate, we should be able to get down to the levels of the signal. And the intensity difference between this signal and the brightest of the contamination is roughly 1,000,000 times, right? So what you see is 1,000,000 times or more stronger than the signal from the first stars and galaxies. And this is the primary challenge of our field. So people who are more technically oriented, just one slide to show what kind of signals we are looking at. And we measure these powers in Kelvin units at different frequencies. But we really don't have to get into the details of this. One thing that I also want to convey here is, given that we don't know what the first stars and galaxies looked like, as a matter of fact, that's why we are studying this. We also don't know what the signal should look like from them, right? So it's a chicken and egg problem. We want to understand something by observing something from these sources, but we quite don't know what we should be looking for. Right? And that's why you see so many colors. These are all different predictions from physics of what these signals should be like. But it's possible that none of them is true. And therefore, then we have to then go back to our drawing boards and start asking more questions. So what's exactly happening at RRI, you may ask? We are trying to build these telescopes. And these can't be off-the-shelf telescopes that we can buy off and use it, simply because, as I said, our contaminations are exceptionally high, right? 1,000,000 times or more strong. So we have to custom build these kinds of things in our own institution and then take them out and observe using these instruments to get down to the accuracies, right? We have to make very precise measurement of what the sky is like. So in an ideal world, we would be seeing something like this. You have these first stars and we have these pristine signals from these first stars coming to our telescope. But of course, the reality is something like this. You have first stars, of course, but you also have your galaxy, you also have terrestrial interference, and you also have your own telescope. And what you really get is sum of all of these things. And then your job becomes to how to subtract each of these components to an accuracy better than 1 part in a million, which is 0.0001%, and then uncover the faint signal which is coming from these first stars. So that's exactly what we do at RRI. And the telescope that we use is called SARAS. These different models are basically different stages of evolution of SARAS. And these pictures highlight a few. These different shapes that you see is all because we again require measurements to be very, very accurate. So we play around with a lot of designs and see how we can make our telescope be more accurate. And that's precisely the reason these days we have started floating this on lakes rather than observing more traditionally like how other people do on land. So it's not only my work. These kinds of efforts are by construction very interdisciplinary, and it does require expertise from very different domains. So we have lots of bright minds here at play. Girish right here in the audience who will talk more about a few other aspects. We have Narendra, Vishaka here and a few other people who are part of our team. We have a very nice handshake between the techniques and the science parts. So at RRI, we almost work hand in hand with different aspects, because you have to design these systems, you have to build them, you have to test it, you have to take it out to the pristine locations, do your observations of the night sky, come back, analyze the data, and see what you can tell of the first stars. So this is a huge range of things which does require expertise from all different areas. And of course, in the recent past, I can't go into the details of this, but in the recent past, we have had very significant results from SARAS telescopes, where we could get very important clues about the nature of the first stars and galaxies. However, this signal, even as of today, is undetected by anyone in the world. And we are roughly, say, 6 or 7 experiments worldwide who are trying to do this, pushing the limits of sensitivity every day. So it has given us nice hints of the nature of these first stars, but we are still to pin down the actual signal, and this is one of the most sought after things in the field of cosmology. So with that, I think I'll close, and I'll request Girish to take up and talk more about what kind of efforts we are doing at RRI in order to get to the required sensitivity. And we'll take questions after Girish's talk then. Thank you.
Thank you everyone for being here Sunday afternoon. Title of my talk today is Efforts at Raman Research Institute towards hunting for elusive signatures from the first stars. Saurabh mentioned about the signatures that we are looking for. As you can make out from the title, we assume that the receiver system SARAS radiometer is already in place, and then it has gone through the laboratory, all evaluations and other things. Okay, so we need to take the radiometer, SARAS radiometer to some place, deploy it, and then observe, collect data, come back and analyze. So where do we take it is a question. So what is the importance of a remote observing site? So Saurabh did refer to some pristine sites that there's a pristine site that is required, and then all the radio frequency interference, and then in this talk, I'll give you an analogy of what happens with very strong radio frequency interference. And then once you have identified a site which is remote, and then is not very far away from civilization, just because it's far away from civilization doesn't mean that it is suitable for SARAS kind of activities. So what is it that we look for in remote sites? So I'll be referring to that. And then we have recently, in the last year or so, we have visited a couple of interesting remote sites across the world, and for really to do frequency characterization of the site and see if it is suitable for SARAS experiment, to deploy SARAS. Okay, and then end with some challenges that we encountered. Of course, at the end, you would all really very quickly, really nicely note that radio astronomy activities does take you to very nice remote places. So it comes with its own challenges. So you'll be able to appreciate that as well. So we all work together in the laboratory called Distortion Lab. Okay. And then one of the major aims of the lab is where we continually design, develop, deploy, trial, and improve a spectral radiometer, learning from previous deployments, and then factoring in those whatever we understand from that, and then build a new system. That is one part. And the next part, like I mentioned, is we are always looking for potential observing sites where we can deploy. And potential observing sites, by that we mean which is radio quiet, relatively radio quiet, and then free of what we call as radio frequency interference that Saurabh referred to. So, I will be telling you more about this radio frequency interference. So, the major activity like is mentioned here is we design and develop all the entire what we call as the SARAS radiometer, right from antennas to analog receivers to digital receivers, and put them all together and then collect data and then come back and analyze. So, basically we are looking at a frequency range of 40 to 200 megahertz. So, what is the importance of a remote observing site for SARAS? So Saurabh did mention about we are trying to detect an extremely weak signal of the order of few tens, a few hundreds of millikelvin present in a background of order of 10 to the power 5 from galactic and extragalactic sources. As if this challenge itself was not sufficient, we have another problem, which is terrestrial man-made radio frequency interference. Okay. So, by this what we mean is all the interference, radio frequency interference which comes from FM radio broadcast, and then various communication system, for example, airport radar or walkie-talkie, police communication, various things, and then emission from satellites, and then emission from certain lamps and lights, and then in addition to all these things, well, we are kind of complaining or cribbing about a lot of interference that falls within our band of interest, like this FM radio, satellite, airport, handheld receivers. This interference which comes from our own systems. Like for example, you have a processor. We had I showed you a picture of a laptop which is acquiring data. Okay. So the processor itself has a lot of clocks and then a lot of switching signals, control signals. They themselves radiate, and then we should not be confusing our signal of interest, and then we should not they should not mimic our signal of interest. Okay. In the next few slides, I'll also tell you how we manage this particular thing, that is interference from our own receiver. So I just want to give you an analogy as to what happens, what is the effect of radio frequency interference from this. So what we understand is about less than 70 dB is something that is comfortable for humans. There's the sound of a normal conversation between people, and then less than 70 dB is safe. But if we just go beyond this, and then I'll just take example of a jet engine at 135 dB. The reason I take this is I'm sure most of us in this audience would have at least once visited the Aero India show, which happens not far away from here. And then it's so nice to see various kinds of fighter jets like Sukhoi or something like that, and then he's simply taxiing and going to the top of the runway, and then once he gets clearance to take off, once he revs up his engine, and then you can see that you will not be able to talk to your neighbor. Okay. So even if you are shouting, you will not be able to understand. So what it means is, just as loud audio frequency signals interfere with speech comprehension in humans, loud radio frequency signals interfere with the normal operation of a sensitive SARAS radio astronomy receiver. So by a sensitive radio astronomy receiver, it has been designed such that it's able to detect 1 part in 10 to the power 5. So it's extremely sensitive instrument, but if there is a very strong radio frequency interfering signal, at times it can be debilitating. Okay, so receivers can go bad. So this is the analogy. So SARAS team is searching for a remote radio quiet observing site, so that SARAS receiver can simply operate normally. Okay, so we are looking for a remote site. So what are the possible places, and then why is it that we want to be far away from civilization? And then it is because we are hoping that there will be minimum radio frequency interference at potential observing sites. The reason why we say it's hoping, because from our previous experience, we said just because it is remote, it doesn't mean that it is radio quiet or it's conducive to deploy SARAS. Okay, so some of the places that we can visit is one of them is Andaman and Nicobar Islands towards the north, and then you can see that the population density is pretty low. Just for reference, I think Bangalore is about 11,000 per square kilometer, 11,000 people per square kilometer. So out of these 4 lakhs, maybe 40% of them stay in and around Port Blair, Sri Vijayapuram. And then if you go far away to Ladakh, where population density is much less, it's in single digits, low single digits, And then the reason why I have shown you these two is the international astronomy community is building a radio telescope. It's what's going to be the world's largest radio telescope called Square Kilometer Array, with a collecting area of about 1 square kilometer. And this coming up in the Western Australian desert area, and then you can see it's almost nothing. Very few people live here. So the low frequency part of this square kilometer array, well, it is coming up in Western Australia. The mid frequency part is coming in the Karoo region of South Africa. Okay, so we see that. So there is a reason why we want to be far away from civilization, hoping that it is conducive for SARAS deployment and proper operation. Okay, so it's nice you can identify remote sites. Just because it is remote, is it conducive? So we need to, what we do is we need to carry out a frequency characterization of a potential site, observing site for SARAS. So we ship our RFI recording system, okay, to the remote place and then put it together. It basically consists of an antenna, which is something similar to this, which which picks up electromagnetic radiation, converts it to electrical signal. It's amplified by some preamplifier, and then through a long coaxial cable, it brings it to a post amplifier, analyzer or spectrum or network analyzer like this, and then there is a recording system. The reason this set is enclosed in what is called a RF shielding enclosure. You remember I mentioned the processors inside and the network analyzer, all of them have clocks and switching signals and other stuff in them. So we don't want these signals to leak and then get into reach our antenna and then come back and be part of our system. Okay, so to prevent that from happening, what we do is we put it in what is called as this, what you see is the black box here. It's a RF shielded enclosure. Okay, so this is the antenna is here. Preamplifier is sitting right below antenna. There is a 10-meter coaxial cable bringing it to this electronics recording system, which is inside this box. Because it's a remote site, we will not have access to power. We power it from using batteries, which we carry. Okay. So this picture is from a remote site near Diglipur in North Andamans, and then this is the spectrum. So by spectrum, what I mean is on the x-axis here is frequency ranging from 5 megahertz to 500 megahertz. On the y-axis is power in dBm. So we find that except for this blip here, which comes from a satellite, the rest of the band appears very nice, and then this is really one interesting place that we want to go, and then we have been there recently, and then we want to go there again and collect more data. So one of the items that was listed in the possible sources of radio frequency interference is lamp or light sources. So we went to another site in Andamans. So when the lights were off, this is how it looked, and when lights on the lamp, lights on this tall lamppost, when they were switched on, this is what it became. So especially some LED lamps, they generate unwanted emissions across the band of interest. So that's the reason why we need to be really away from all these, and then as remote as possible. That's what we mean by pristine from the point of view of radio frequency interference. Okay. So this is just a video. I'll just draw your attention. Please focus on the left-hand side of this instrument. So after some time, we'll get the lights switched off one by one. Okay. So a commercial instrument is already struggling, which is supposed to be having a large dynamic range, which is supposed to measure large. So that's already struggling. So there's no way a sensitive instrument like SARAS would survive in this expense. Survive meaning do the job that it is expected to do. Okay. So lights are switched off. And then we come back to thing. So it's much better. It's almost like the plot you see on the top left here. And then the ADCO range with the instrument was struggling, so that's gone. So we requested them to start switching on the lights one by one in the surrounding area, and then you can see things are going bad, and it will get back to this situation when especially the light on the tall lamp post when it comes on. Yeah. So with a lot of these site characterization strips and other things, many of us have kind of graduated, if I may say that. Just looking at the first spectrum here, more or less we can estimate or assess what kind of a site it is. We don't really have to look for long-term data collection and things. So that's how it's back to now that once the lights are on, and then the system is again struggling, saying that it is ADC over range, which means it is going beyond its limit. Okay. So what it means is, even if a potential observing site is remote, its RFA characterization can throw surprises, just like you see here. So so typically one of the requirements is we want to be away at least by a few kilometers from such light sources. Okay. So we want to really go to remote sites. So one possible site is really this place called Svalbard archipelago in the Arctic region, and then it belongs to Norway. And then thanks to Saurabh, I got an opportunity to visit this place with the RFA characterization equipment about 6 to 8 months back. So this region is blown up here in this. So Longyearbyen is the administrative capital of the place, and this place is called Ny-Ålesund. This is the world's northernmost permanent settlement. There are a lot of research stations from about 11 or 12 countries and 20 different groups carrying out research activities, of which about 3 or 4 countries do that round the year. Okay, and then just for reference, Bangalore latitude is about 13 degrees north, and then about 77.5 degrees east is the longitude. So it almost swaps the positions. Latitude of Ny-Ålesund is of Svalbard is 74 to 81. Of Ny-Ålesund is about 79 degrees north, and then longitude is about 10 degrees east. So we think we are really in a remote place. Okay. And again, one of our metrics is population density, and it is comparable to the Western Australian area, 0.04 persons per square kilometer. So I'll have some very interesting slide on Svalbard in the next few slides. Okay. So Ny-Ålesund, which is somewhere here, is about 1,200 kilometers from North Pole. Okay. So it is well within the Arctic Circle. This is the Arctic Circle. Arctic Circle has the latitude of around 66.3 degrees, 66 degrees 30 minutes. Okay. And then Ny-Ålesund is something like this. That's how it appears. There is a settlement area, a town area, and there are a lot of buildings here which belongs to various, it belongs to a company called Kings Bay, and then many research institutions from various countries, they have occupied they have taken up some of the buildings here, and then where they carry out research, especially in study of climate change study, and then atmospheric sciences. And India has its permanent research station called Himadri here. Okay. So slightly more about Himadri. So because we have this Himadri station, we could go there and then have a base. And then it is India's permanent research station located in Ny-Ålesund, Svalbard. It has been operational since 2008, and scientific teams have traveled to Himadri only in summers. That was till the end of last year, that is about December 2023, only April. That is because daylight was available during summers, and then when temperatures were above freezing point, and then people could go out and do their field experiments. So, although automated observations continued during winter, field experiments were not possible. In 2023, India decided to maintain a year-long presence at Himadri and to become only the 4th country in the world to do so. So, winter expeditions aim was to, they wanted to address the data deficiency during polar nights, especially in atmospheric sciences, space physics and biological sciences. So, I had an opportunity to travel with a group of three other people to this place, and I was part of the, really proud to be part of first ever winter scientific Arctic expedition from India. Okay, and then this is the place where we were staying. This is Himadri station, and then I think I spent about 1 month here. I carried the RFI characterization equipment there, and then about 1.5 kilometers from this place, this is a laboratory called Gruvebada laboratory from Himadri is somewhere here. Okay, so it's about 1.2 kilometers from this is Gruvebada. On a rooftop of this laboratory, we are set up this RFI recording system. I'll show pictures of them. I told you the Svalbard archipelago, there's some interesting facts about them. The 1920 treaty allowed Norwegian sovereignty, so it basically belongs to Norway. Is the world's northernmost permanent settlements. Although further north there are settlements, they are not permanent. So this is considered to be the world's northernmost permanent settlement. It is said that polar bears outnumber people. So there are about 2,500 odd people, and they expect more than approximately 3,000 polar bears. Okay, so king of Arctic. So due to harsh conditions, there are no trees or tall shrubs. Plants that grow here are less than 10 centimeter in height. And interesting, cats are banned in Svalbard, and then it is illegal to die in Svalbard, and giving birth is discouraged due to lack of medical facilities. And then what is called as civil polar night. Civil polar night is when sun is about 6 degrees below horizon. So it lasts from November to January. And then Svalbard, like all of us know, Norway is a land of midnight sun. You will also have between April and August, sun never sets almost. So these are pictures taken in Ny-Ålesund as soon as when we had moon, and then when it bathed Ny-Ålesund town in moonlight, that's when we could see the surrounding peaks. We had only seen them on Google Maps, so we got to see them because of this. And then this is moonlight reflected from the waters of Greenland Sea. Okay, it is just adjacent to Ny-Ålesund settlement, and these are some of the pictures from the settlement. So when you're up in Arctic, one of the major attractions is Northern Lights. Okay, so we got to see them almost every day, and then although these pictures really make it interesting, and then videos also that you might have seen, it makes it interesting. There's nothing like viewing them with this camera. So if that was about Svalbard and then a remote place. So like I mentioned, Ladakh is also a remote place. What you see in this region is a region called around Hanley. Okay. This is where the Indian Astronomical Observatory is present. It has its various telescopes there. And so if it was polar night and that was a challenge, and there was no sunlight and then cold temperatures, again here it's pretty cold. And then other challenge which comes in here is about altitude. It's on the average it's about 4,750 meters or around 15,000 feet. So the additional challenges which comes in here, I'll have a couple of slides on them later. So we call this as waterfall plot. Basically what it is saying is in the frequency range of our interest and as a function of time, how the interference and then what is the strength and whether it is continuous or like what you see here, for some time it is not present, again it's present, for some time it's off. So this gives us a bigger picture of strength of interference, and then whether it is continuous or periodic or sporadic, whatever it is. So this is from Hanley region, and then except for the known interference signals like from satellites, amateur band or the satellites, we see that in our band of interest is pretty clean, and then it is quite encouraging for us to deploy SARAS here and do science observations. So to find remote sites, at times we need to track at the altitude of 4,000 to 5,000 meters, and then maybe we took Robert Frost, the road not taken pretty seriously, I think. Okay. And then at this altitude where doing your normal chores is difficult, so we need to put things together and then be ready to deploy. And then we also had an opportunity to row at 16,000 feet in one of the lakes there. And after such a hard day, as you head back to your base station in Hanley, Indian Astronomical Observatory's guest house there, sometimes nature has its own way of removing all the whatever you have undergone through the entire day. So looking at such wonderful events, it's really nice that we could witness such things. So maybe SARAS is the only CD, the Cosmic Dawn EOR experiment in the world that has been deployed at such a high altitude. Okay. So you may be wondering why this pulse oximeter, which became so famous or infamous, depending on how you see during COVID time. The reason why we have this picture is, the reason is this. So at sea level, if the percentage of oxygen in the air is about 20.9 or say 21%, as you go to the peaks of Hanley and then deploy your instrument, SARAS equipment there at around 16,000 feet, it almost reduces by half. Okay, so you are basically struggling to, the body is struggling to get the required oxygen. So as soon as you go there or even reach these heights, you can feel your heart is pounding away, and then trying to supply the oxygen so that you don't pass out. And then we have seen people, and then we have had people who have struggled, and then that's the reason why we routinely keep monitoring our SpO2 and then heartbeat rate and other things. So that's the reason why I included this picture here, which is misfit if you are thinking that way. So if Northern Lights is an attraction in Svalbard, given its altitude, Hanley region, like many of you would know that India's first dark sky reserve is in Hanley. Okay, so we, like Saurabh briefly mentioned, that you get to see some of the best skies from this place. And then this is a picture from Dorje Angchuk, an award-winning astrophotographer from Indian Astronomical Observatory, Hanley. And then this is light within our kitchen tent where we had deployed, and then this is our vehicle here, and then our other deployment gear, they're all here, antennas and our tents where we stayed. So this is such a wonderful thing. And we almost get to see this surreal sky, especially coming from Bangalore. To see such things is really fantastic. Okay, so that was about cold desert, Svalbard, remote place, and then something familiar, it is Andaman and Nicobar Islands. So when you go there, it is more like you are somewhere traveling somewhere in Western Ghats, something like that, with a lot of greenery, forests, and then turquoise water of Andaman Sea on one side and Bay of Bengal on the other side. So this is one place in a place close to Diglipur in North Andamans, where we had deployed recently. So this is the team putting SARAS units together, and then Saurabh and I were trying to figure out in this lake which is the best place to deploy our antenna. So it's deployed, and then Antenna collects this electromagnetic signal, converts them to electrical signal, and then there is an analog receiver which amplifies and does signal conditioning, and then there is this fiber which brings the signal over this fiber to the digital backend unit, which is on the shore, about 150 meters, 125 or 150 meters from shore. So then there is this, we are checking out antenna for evaluating its performance, and then the digital receiver is in place. Okay. So when everything is ready, so when we want to do this, this fellow comes out saying, okay, you are trespassing. So like you can see my hand here, digital receiver, which basically is the master controller of the entire SARAS radio meter. So when you start this, you can control all the switching in the analog receiver and other things. So the control signals go over those fibers, and then analog signal is brought back, it digitized, and data is collected in a laptop which is here in the top tray here. So this was left open. So we quickly close this, zip the tent, and then try to get rid of that. Okay. So this is all done. And it was monsoon time. There were already a couple of rains which had already come in that region, and that is when we understood that from locals that when all the snakes come out of the forest and then start moving all over the place. Okay, so this we understood was an Andaman crate, and then there was a doctor who was visiting, a medical doctor who was visiting the site. And then he kind of warned us, said, get bitten by any snake, don't worry, I'll send you back to Bangalore safely, but not this guy, Andaman crate. So if you're bitten by this, please take a phone call to have the last conversation with your near dear ones, and then say goodbye to life. Okay. So they did not have antivenom there. Okay. Okay. So you survive, sorry. You survive all these and then come back to your room to rest, and then this guy was my roommate, giant Andaman centipede. So he would simply be walking all over, crawling all over the place, and then maybe because our guest house was at the edge of a forest, and then this was his home, and then again I was kind of trespassing. I was occupying his place. So not knowing what to do, I simply taped the gap between door and the floor. Just to be safe. We understand again the local story is that it's extremely painful when it bites you, although not fatal. Okay, so you need anesthesia in the area where it is bitten. So the best is mix salt and kerosene and then apply. That's the anesthetic to reduce your pain or something like that. Okay. So very interesting and challenging. Each place, whether it is the remote Svalbard or Ladakh or Andaman, each one in addition to challenges of radio frequency interference and then mitigation and then deploying SARAS, collecting data, these are additional challenges, very interesting ones that you encounter. Okay. So this slide is, let's look at the date, it is around 6th January. Okay. So I told you that it was December, January when I was in Svalbard, and then it was polar night. As you can see from this picture, the RFI, the antenna for RFI collection is, it was deployed on the rooftop of the Gruvebada lab there, and then just beneath this antenna here in the room, we have the data collection recording system, the RFI recording system. Along with the battery there which is powering the electronics inside, and the shielded enclosure which I referred to earlier. Okay. So how does it feel to be out there? I think this video is just to give you a flavor of how it feels to be. So a couple of them have bright headlamps there, and then they have what they call as high-vis shirt there, so that when they are walking in New Ulsan town, vehicles don't hit them. They have very bright reflective garment there, high-vis. So these two people from Kings Bay, we are trying to put the antenna together and then make the connection from antenna to the preamplifier, and then use the 10-meter cable and then bring signal to this place. It is coming through this window here, and then antenna is on top of this, on the roof of this block here. So I want to draw your attention is just for a moment, if you can see the background, it's very dark. Okay, so if we were to switch off the all the headlights there, it's pitch dark. Believe me, I mean, I think the video, there's an audio here where a colleague of mine is cautioning me. It's very slippery slope there, and then if you were to just slip or fall from this place, you would be dropping down about 12 to 15 feet and then into snow. Okay, so we need to be extremely careful. And then you can see these two people are just making sure that, and then it's very strong winds and snow, and they're just making sure that the antenna is not carried away by wind, even though it's a heavy antenna. Okay. And this is the guy who is making this video. His, you can see when he just turns away, it's so dark in the background. And then, if you see here, it is time is 1:45 in the afternoon. So that's what polar night is. That's a challenge that comes with. You can see on the right side, it's so dark. So there are a lot of people. Newspapers from here, and then various science journals who are getting in touch with me saying that how was their experience and things. Everyone said, please share nice pictures. What picture do I share from here? And then with one of them I simply said, okay, I had a video thing. We have very good internet connection here, very high speed internet connection in New Ulsan. And then I told them, I'll just switch off the lights in this laboratory, and then said, sir, are you there? They asked me. So they could not even see that, they could not even make out that I was there. It was so dark. Like you would expect, it is a bit, it's quite challenging, because to make all the connections, if you may just recall the block diagram I showed, there was a filter just before the preamplifier. So we need to keep changing filters and then collect data. So there's no way you can do the connections with your gloves on. You have to remove this, and at the end, I had first degree frostbite after this. That's okay. So the 10-meter cable is being sent down so that it can be collected from here and then interfaced with the recording system. Okay, maybe I'll stop that. I was just joking with Subbu. If you thought that, okay, you're a lucky guy, you went to such nice places, you got to see auroras and other things. So I just want to draw your attention to this. Okay, average temperatures during our about 28-30 days of stay there was about -15 to -20 degrees. Just one day, I think 5th of January, with wind chill temperature, it went to -40.5. So given that the temperature is generally in Bangalore is going up every summer, so it's more or less a sign change. So I should also be talking about this. We did manage to get, do the frequency characterization of the site, and then this is again a waterfall plot from Gruevada lab data, the data that we have collected. And then the quick conclusion from this is in the frequency range 100 to 200 megahertz, which we call as upper band for SARAS operation. That is very encouraging. We do not notice any strong out of band interference on either side of that, but for this one strong signal at 172 megahertz. So, this 172 megahertz, it ranges from 167 to 172. This is something that everyone who is staying in New Olsen has to use it. So, the moment you step out of your station, and then if you are going for field experiment or something, you need to carry that walkie talkie, so that if there is any emergency, you will be able to contact your station and then get help. And also there is the equivalent of emergency button. You press that, there is always one guy 24/7 who will come and help you if you are stuck somewhere. Your vehicle is, you need to be driving yourself from Himadri to Gruvevada lab, you need to be on your own. So, if there is any problem, you can worst case call the emergency guy and he will come and rescue you if you are stuck. So, the conclusion is RFI scenario is acceptable for SARAS science deployment, and then if everything goes well, the team should be there end of the year, December or January. So, I think with this I will conclude. Thanks for your time and patience. Hope I was able to give you a flavor for how these deployments go in various remote places. So, although it is interesting, a lot of challenges involved in terms of working conditions as well as other things that I mentioned. That is it. Thank you. Thank you.
Hi, so my name is Ashwin Devraj. I am a PhD student at Raman Research Institute. So I'm finishing up my PhD now, and my primary research interest is in looking at neutron stars. I'll tell you about what neutron stars are in a bit briefly, but I use X-ray data or X-ray information in X-rays to understand these neutron stars. Okay, so the main topic here, as far as X-rays are concerned, we are going to look at polarimetry using X-rays. What is polarimetry in general? What is polarimetry using X-rays? Where is it needed, and what causes it, and how does it happen? These are the questions I want to address. So, I have divided it into two parts, the talk. One is the physics aspect of it, and then moving on to the astrophysics of it. Okay. So, I very often get asked the question, if you want to do astrophysics, what is the basics? Like, how do I get into astrophysics? How do I do astrophysics? And if you ask any astrophysicist, they will give you the same answer: be good at physics first. So, developing on physics on a much larger scale is what astrophysics is. So, first we need to understand basic physics of what happens, and our basic physics involves the interaction between charges and electromagnetic radiation. Meet Mr. Charge. For our explanation, it is an electron, and electrons, as we know, have a negative charge. Okay? It has a friend who is a proton, heavier and has a positive charge. Okay? They have another friend, a neutron, okay, which is neutral. It's heavier but neutral. Together, all of these come together and form atoms. Okay? When they're all together, if there's equal number of protons and electrons, you have overall charges 0, right? Charge neutral. So, typically what we deal with, or what we see, what we are made of, all these things are all atoms, and they're all charge neutral. It becomes interesting when you have charges involved, meaning they are not neutral. Then these things behave very differently. Now, charges are predominantly affected by two things: electric fields and magnetic fields. Okay? And their interplay is what gives rise to all the phenomena we see around us. There is also gravity here, but gravity does not cause radiation. But what I want to say is what happens when charge interacts with electric field and magnetic field, and then in principle what it does as a consequence. Okay? Neutrons, I mentioned, right, are neutral, so they are not affected by the electric and magnetic fields. Electrons and protons are. Here is at the end of this talk, if you are going home, I want you to remember one thing. I want you to remember this statement: accelerated charges radiate electromagnetic waves. Okay? So, the radiation that you are seeing, radio waves, you heard of microwaves, you heard of X-rays, all of these are radiation. How are they created? It is created through the acceleration of charges. If you accelerate a charge, it will radiate. This is the sacred principle that you need to just keep in mind. Okay? So, how do we accelerate charges? I mean, if you want to accelerate someone, you go and kick them, right? So, they'll suddenly get a jerk and they'll move forward and fall. That's an acceleration. But how do you do it for charges? You can't tie a string and pull it fast, right? You accelerate it through electric and magnetic fields. So, this is a small video that shows how if an electron accelerates. So, there are many ways of accelerating it, right? You take an electron, you drag it suddenly, you apply electric field which will drag it suddenly, and then that will accelerate it. You make it move up and down, it will accelerate, right? Because its direction is changing constantly, its speed is also changing, so it is accelerating. So, this is a video showing how an accelerated charge will produce radiation. So, this charge is moving up and down, okay, and it is producing these red waves that you are seeing as the electric field. What you are seeing parallel to, perpendicular to it in the green is the magnetic field. So, electromagnetic radiation is a combination of electric fields and magnetic fields perpendicular to each other, and then there will always be perpendicular direction which they are propagating. Okay? So, now you can see this here. The frequency at which you oscillate this electron is the frequency of radiation you will produce. Meaning, if I want to produce radio waves, I will oscillate it slowly. Okay? If I want to produce X-rays, I will oscillate it rapidly. Okay? The frequency is basically how many times does it oscillate within 1 second. That is how we talk about electromagnetic radiation. It is a wave. And the frequency is how many times does it oscillate. Okay. One other thing I want you to notice here, you can see there are multiple lines here in different directions. So, if I basically have one charge here and I move it up and down, it will produce radiation in all directions. And I just pick out one of these things and I go very far away, right? There actually is one specific plane in which it is vibrating. The electric and magnetic fields, electric field is going this way, magnetic field is going this way when you go very far away. Right? So, just keep this in mind, just consider one of these things and just keep it in mind. We will come back to it in a minute. So, what is electromagnetic radiation? It is basically magnetic and electric fields varying with time. You can see this here. Magnetic fields are varying in one direction, which is here, and electric fields are varying that way. The number of times they oscillate in 1 second is the frequency. And how high the frequency is, how many more times it oscillates in 1 second will tell you the energy of the radiation. So, now what happens when you take these electromagnetic radiation and you throw it at charges? So, I said charges produce electromagnetic radiation when they accelerate, right? So, how did you make the charges accelerate? Apply electric magnetic field. Okay. Now, radiation is produced, there is one charge sitting there silently. It goes and hits that. What will it do? It will make the charge move up and down. It will accelerate the charge. And then what will happen? Now that will radiate. Okay? So this is how it works. So think about it this way. When you're looking at the night sky, right, there are these stars. So light is produced from there. That light, those photons are reaching your eye and making the particles in your eye move up and down. And those signals are imparted to your brain unhindered, from all the way from how many of light years away. Okay? So, the point is the reason you are able to detect it is that the electrons in your eyes have moved up and down and created that electrical signal so that you can actually identify that's happened. So, if it does not interact, it just goes through. For example, you do not see in infrared, it just does not make it work, or lower wavelengths, microwave. You are seeing invisible because it's interacting, making the same changes here. Anyway, moving on. So, what happens in a bulb? So, I just told you something. Accelerated charges radiate, but in a bulb it's made of atoms. They're all neutral, right? Why is it radiating? So the principle again is that you need accelerated charges. So first thing is that when it is coupled together, you first separate it out by applying a huge amount of voltage across the ends, and then that will heat up the tungsten. And then once that happens, the electrons pop out. And now these electrons, like I said, there is an electric field applied at two ends. So they get accelerated and then they radiate. Okay? So accelerated charges radiate. Now, I showed that earlier there are these individual lines that you are seeing in one direction. If there is one single charge accelerating, moving up and down, there are these individual electromagnetic field variations that you are seeing. Now, let us say that right next to each other, I throw many charges and make them move up and down. And then I go very far away and I look at the light coming from the collection of these charges. Will I see the charges, will I see only one direction in which electric field is moving up and down, or multiple directions? So all the things are contributing to light. So if one set of electrons are moving in this plane, one set of electrons are moving in this plane, they'll all produce electric and magnetic fields according to how they're moving. So what I ultimately get is a combination of all of those things, electric fields and magnetic fields oscillate in all directions, and then I see unpolarized light. Now let us say I have a device which can cut out everything else except in one plane. Then that is called a polarizer. In optical case, you would have seen this, and I'll come to an example in a minute. But what it does is it restricts a very specific polarization to come out. It means that when you have all possible orientations of these electric fields, you're identifying one specific plane, and then that plane in which it's oscillating, that will be the plane of the polarization, and then that light will be called as plane polarized light, linearly polarized light. Okay? So here it is at 90 degree this way, and here it is perpendicular to that. So these are two polarizers. Now can you imagine something? I said that all this contains all kinds of vibrations, all directions. What happens if I put this polarizer after this? Can anybody guess what will happen? Sorry? You don't get anything, because there is nothing oscillating in this way for this to capture and let out. So two polarizers perpendicular to each other will cancel out all light. And this we use, I'll get to an example of where we use in a second, but little more about polarized radiation. How do you produce polarized radiation? So like I mentioned earlier, I have a bunch of electrons all moving around randomly, and they're all emitting radiation in all directions. So if they're moving randomly, the radiation they emit will be unpolarized, right? Because they're coming from all directions, they're moving in all directions, there's no specific direction that's interested. If you have one single electron moving up and down, the radiation that comes from it will be polarized. But when you have a collection of these atoms and electrons moving around randomly, and you're combining all the light that comes from them, that will be unpolarized light, right? Because there's no specific clear direction. So I would say the emission is isotropic, same in all directions. Next, if I apply an electric field to this, there are electrons. Whatever they were doing, they are vibrating here and there, whatever. I'm giving them a preferred direction in which they want to move. And suddenly, they will do their vibration, but in one specific direction. So the radiation that comes out of that will be polarized. So the breaking of isotropy, same everywhere. When I take that away, suddenly I get polarized light. I give a preference. You need to see that, come back to this diagram, animation. This line, this plane in which it's oscillating, choose one, and that is the plane of polarization. Okay? So when I am looking at this red plane, that is the plane of polarization. This radiation will be polarized. When I look from very far away, I'll only look at one of these things. Okay? When I go to this box of gas and I apply an electric field, I make all of those things oscillate in the same direction. They're not moving randomly anymore. So the radiation that comes out of them will be polarized. Okay? So where do we really use this? The main idea is that second point. First point, accelerated charges radiate. Second point, anisotropy gives rise to polarization. And I'm not talking only in X-rays, I'm talking for all wavelengths. This is how it works. So what's the point of studying polarization? polarization is used everywhere. The idea or the concept and the importance is a lot. Have you heard of Polaroid glasses, those cooling glasses that you wear? They cut off half the light, right? So if you have unpolarized light, you're cutting off all the light that's oscillating in every plane except in one direction. So 50% of the light is cut off. So when you wear these as sunglasses, you do not get as much intensity. 50% of it is cut down. That's why you have polarized glasses. Second thing is that this is a display, what you're seeing here, like a monitor or a watch or any of these things. What happens there is you have liquid crystals. You have small, each liquid crystals are basically these small objects, very tiny. And then when you apply electric fields to them, they will orient themselves. They will allow a portion of light to exit, and then when you rotate them, they will not allow. Okay? On top of that, when you put a polarizer and you rotate the liquid crystals by applying electric fields, only some specific lights come, and that's how you're getting all of these things. LCD, liquid crystal display, right? So there is one polarizer there on top of the screen, and then you're introducing a Polaroid. So I asked a question a little while back, what happens when I put two Polaroids on top of each other at 90 degrees? You mentioned the light gets killed completely, and that's what's happening here. When it is this way, the polarization axis of the Polaroid as well as the LCD are both in the same line. When it's 90 degree, it becomes black. So polarization, you can see that it's being used for the liquid crystal display. Where else? One other example I can tell you is when you go to movies. The 3D effects that you see is based on two different polarizations that are there. So the depth perception is contributed to it. One eye gets one set of type of polarization, the other eye gets the other type of polarization. And depth perception. If you remember earlier, there used to be different colored glasses, cyan and red, green and red, and things like that. And that would give you a certain weird feeling when you're watching the movies. But here, with using polarization, left circle and right circle polarized light, you get a more clear 3D effect. Okay. So now we move on to the second part. And the idea is about astronomy in general, and then moving on to specifically why X-ray astronomy. So Saurabh had shown a slide about how you have all kinds of, all the wavelengths, how important they are. He showed you a slide where, you go from radio to X-rays, and Milky Way looks very, very different in different wavelengths, right? And X-ray and astronomy or astrophysics is a place where gravity is king. It reigns supreme. And everything that you talk has to be in context with this. And when you go further in smaller regions of that, then you start talking about the other processes that happen. But gravity is the ruler. So why look at X-rays? Why look at the universe in X-rays at all, right? So here is the thing, when you look at an optical, the first telescopes that were made were an optical, right? This is how a specific galaxy looks. When you, by the way, we can look at a very narrow range of this, okay? In the grand scheme of things, we are deaf and blind. That needs to be understood. So when you're looking at the thing in optical, invisible, you're seeing a certain, this is what it looks like. When you start looking at infrared in the electromagnetic spectrum, go to lower energy, meaning lower frequency, this is what the galaxies look like. And when you go to even lower frequencies, this is what it looks like. Now come to the highest energy, X-rays. If you look only in X-rays, this is what it looks like. Can you see that these are two completely different images? If I showed you this on Monday and showed you this on Wednesday and asked you what are these two things, you'll never come up to me and tell that they're the same thing. They're two completely different objects. But the analogy that Saurabh also gave is that a bunch of blind people trying to figure out what the object is in the elephant. You need to put all of these together to see. The cause for emission X-rays is very different from what emits radio, right? So the idea is to put all of these together and do it in a multi-wavelength. And that's the idea of combining all of these. And our eye can only see a very small range of light over here. Okay. Now, just to get an idea, before we move on to what neutron stars are and what other things are, to get an idea of the scale of things. If the sun is this large, Earth is this tiny. Okay? In the grand scheme of things, the fight you had yesterday morning has no relevance. Okay? The point is that how do you construct this sun? How many Earths do you need to put in? Like this, let's say you take something, the volume of the Earth, and you start filling up an object like this. How many Earths do you need? You need 13 lakh Earths to fill that up. But here is some interesting thing I want to say. The sun is so massive, and you need about 3.3 lakh Earths to fill the sun. Mass, that is how massive. But the sun is not, even though sun is so massive, it is not as dense. You know the density of the sun? It's as much as water. It's full of helium and hydrogen and all of these things. But the density, number of particles, number of grams per centimeter cube is 1 grams per cc, which is just as much as water. It's 1.4, but it's very close to the density of water. I mean, the density of this ground is much higher, but the point is that the sun, the temperature is also much higher. They're all separated out, and the density is as much as water. Now I want you to think of something. I want you to imagine that you are compressing this entire thing to a small area. The mass is the same. The number of all those particles are there. Somehow you're compressing, pushing it together with in some way to a smaller and smaller size, to the size of the Earth. Okay? If it is almost approximately the size of the Earth, you get something called as a white dwarf. And if you compress it to the size of Bangalore, in fact, Bangalore has become much larger now, about 10 kilometers in radius, right? Then you end up with something called a neutron star. So just keep this in mind. So what are these compact objects? These are end stages of stars that evolve. So stars are bright because of gravity, their gases are being held together, and then they're put together, and then they're being compressed by gravity. Because of that, fusion happens where small atoms of low atomic weight combine together to form larger atoms, right? You have hydrogen combining to form helium, then helium combining to form higher elements. This is what happens. And then when they combine like this, they produce radiation, and that's what we see. That's why the stars are bright, they're shining. So what happens when you can't fuse them anymore? What happens when you don't have enough energy to combine these atoms? They stop and they collapse, right? So radiation they're combining together, gravity is pulling them in, but radiation is keeping them, pushing it out to make sure it doesn't fall. There's an equilibrium. Radiation being produced is stopping them from collapsing. So that equilibrium, when it goes away, when there is no fusion producing radiation to keep the thing stable, it will all collapse. The entire mass of the sun will collapse to a region as small as the size of Earth. And I just told you need about 13 lakh Earths to fill the volume of the sun. That entire volume reduces to 1/13 lakh of it, right? That is a white dwarf. If it is heavier, if the fusion has happened, more fusion has happened, more higher elements are fused, then it will collapse to even smaller radius, the size of Bangalore, right? So the radius of Earth is about 7,000 kilometers. 10 kilometers and 7,000 kilometers. Just can you imagine the difference? So the entire mass of the sun compressed to that small region is what happens when you end up with a neutron star. Now if it collapses further to an even smaller point, you end up with black holes. These objects have slightly different properties, and where black holes are, you watch movies like Interstellar, so radiation, it's so strong, the gravity is so strong, even light bends around it, and if it goes through it, probably does not escape. My specific research interest is around neutron stars and how they interact with the matter around. Because these neutron stars are massive magnets. Okay, their magnetic fields, to give you an idea, the fridge magnet, let's talk about Earth has a magnetic field. The magnetic field of the Earth in some units called Gauss is about 3 or 6 Gauss, within 3 and 6 Gauss. The fridge magnets that you have will probably have about 1,000 Gauss. MRI machine will have about 100,000 Gauss. Okay? So I'm just scaling it up slightly. You know the magnetic fields of neutron stars typically? 1 followed by 13 zeros. That's how many Gauss? 10 power 13 Gauss or 10 power 14 Gauss. They're massive magnet monsters in the universe. And you understand, these things are interact with the matter around them in crazy ways. Okay. Having said these things, I want you to get to one other point of why do we even have to look at compact objects in X-rays? Like, why not look at it in optical? The reason is the following. Firstly, all the fusion has stopped. All the light that you're seeing, like the sun, it stopped fusing. So fusion is there is no direct way of looking at it. You won't see it in optical light. It stopped producing that radiation. There's no radiation that escapes from the surface anymore. And black holes don't emit any radiation. They're completely absorbing everything that's coming around it. So how do you see them? So to understand the principle of that, why we choose X-rays to look at it is the following. Now, have you seen this? You take a ball and you drop it from a height. Okay? You probably pick it up and you don't see much. But you hit it hard, and you hit it hard multiple times. What happens? What do you feel? Anybody? The ball becomes hotter, right? You feel the heat in it. You can't see the heat in it, but when you look at it through infrared glasses, you start seeing it becoming hotter. Now, let me make an exercise. I am saying that you're dropping it on Earth with whatever mass there is. Now, Jupiter, which is 300 times more massive than the Earth, you need 300 Earths to make Jupiter. I compress that entire mass to the size of the Earth, and I drop it from the same height. Now, mass is higher, the ball falls on the ground, it will become hotter, right? Because the gravitational pull is much higher. So that potential energy is getting converted to kinetic energy. When it hits the ground, it's giving away that kinetic energy, and then it heats up. It's literally like you taking a ball and hitting it with a hammer. That same amount of energy can be produced by dropping it, right? So when you go and hit a hammer on a rubber ball, it heats up. Now what happens when I do it for Jupiter? So for Earth, it's probably emitting in infrared. Jupiter, it's 3 times higher, so higher frequency of radiation. Now what happens if I compress the entire sun to the size of the Earth or smaller and then drop that ball? That ball will reach half the speed of light. Okay? So if it reaches half the speed of light, can you imagine the velocity, how fast it's coming? It takes 8 minutes for the radiation from sun to reach the Earth. It will take twice the amount of time for the ball to reach the same distance. It will reach such high velocities, very, very high energy, and that will start producing X-rays. By the way, when the ball falls, it will be completely ripped apart. All the atoms will come apart and electrons will come apart, and they'll all hit the ground all at once. And then that energy that it produces will be X-rays. Just like how the ball is producing infrared over here when it's hitting the ground, those will produce X-rays. And that's how strong the gravity there is in neutron stars and black holes when it absorbs the material. This is why we are looking at these objects in X-rays. So if you have an isolated neutron star sitting somewhere, can you really see them? No, you can't. It's not easy. It depends on what process is happening, but this accretion process is when you have one object, neutron star, and one main sequence star, which will supply material to it. You have a sun-like star, which will give a material, and then you have the compact object, which will burn it. Then you'll start seeing it. Okay? So this is an example where you have a compact object, like something like the sun, and then you have a neutron. If there was a neutron star nearby or something, it will pull all that material, it will form a disk around it, and then it will burn all that material, producing X-rays. And that's why we are looking at it in X-rays. And I told you something earlier, that isotropy will result in unpolarized radiation, anisotropy will give you polarized radiation. So where is the anisotropy? I said neutron stars are massive magnets, which means the way matter will go onto the neutron star, fall onto it, there is a preferred direction. The way it gets burnt, there is a preferred direction. The way it's emitted, there is a preferred direction. This anisotropy, this break in isotropy is what causes polarization. See, when you're looking at this, the light that's coming from here, right, you can't really tell the polarization of it. But I bring a Polaroid, then I'm able to recognize it. So by bringing a Polaroid, I can really tell what the technology is being used here. So it gives you more information about what there is apart from just the visible. I'm separating out that all those photons of light into two parts. And then I'm trying to understand what causes these individual parts. So I get a better insight about this. This is what is called an active galactic nuclei. There is a supermassive black hole in the middle of the galaxy. When that burns all the material and emits, that will also produce polarized light, because again, these are not spherically symmetric, right? There's a certain direction you can say, jets are in this direction, disk is in that direction. When light from this gets emitted onto the disk and then gets scattered out, there's actually a directionality I'm giving you. It's not uniform in all directions, like the sun, for example. It's coming spherically symmetric. Right? So that's why we expect polarized radiation, and we want to look at X-ray polarimetry. One important point here, unlike visible light, where you have lenses, light passes through it, you bend it, you focus it, and you do all kinds of things. You have polarizers, which is going to separate out these polarizations. In X-rays, the X-rays do one of two things. They will either pass through or they will get absorbed. Okay? You cannot manipulate X-rays as easily as you're doing optical light. So the technology that you need, the common sense question will be, why don't you have X-ray polarizer? Just put it and send it on space, no? But then that doesn't work, because X-rays either get absorbed or they pass through. So you need more complicated, sophisticated technology to deal with it. So this instrument, Polix, was built to look at these compact objects in X-rays so that we can understand what's really happening in some of the processes there. So Gopal Krishna will continue from here. He's an engineer who is involved in Polix right from the beginning, and he will tell you of the details about the instrument and the working and things.
So I will be mainly focusing on how we designed the Polix instrument. So Polix stands for Indian X-ray Polarimeter, and the XPOSAT stands for Polarimeter Satellite. So Professor Biswajit Pal is the PI for this instrument. Now, so far only 2 X-ray polarimeters have been flown. So first one is IXPE, which is flown on 21st December 21, which is by NASA, and the second one is from India, which is flown on 1st January 24 by ISRO. So the IXPE works from 2 to 8 keV energy, and our Polix works from 8 to 30 keV energy band. So both are used for studying polarization, which is degree and angle of polarization of celestial X-ray sources in different energy bands, and they provide information about the X-ray sources. Polix is an unique instrument with proportional counter based detectors and a rotating satellite while observing X-ray sources. This is the uniqueness of the Polix instrument. This is the entire satellite. So this is the Polix instrument, and this is the EXPECT instrument. EXPECT is designed by ISRO and Polix is from RRI, and this is the entire satellite bus. So EXPECT stands for X-ray polarimeter, which is from Space Astronomy Group of ISRO. So where we observe is over here. This is the 8 to 30 keV band here. Okay. So our instrument observes in this energy band. So this is an example. So where the AM radio, FM radio, microwave, they were all in the higher frequency side, and in the higher, they are in the lower frequency side. In the higher frequency side, we have X-ray, and even human beings will be emitting the infrared waves, which you can see through the night goggles. You would have seen in the movies people watching, in the night time how people are moving out. So that is one example for infrared, and for visible light, the light bulb is the one of the example. So now why we have to go to space for studying the X-rays? This is because X-rays are observed by the Earth's atmosphere. So because of that, we have to put our satellites above, about some 200 to 300 kilometer above our Earth's atmosphere. So visible light reaches Earth, and some of the infrared, infrared also doesn't reach, but radio waves will be reaching to the Earth. So, this was designed in collaboration with ISRO. It is completely developed at RRI, and we will be discussing different aspects of this design. So, this is an instrument to measure the polarization of X-rays from celestial sources, which I already mentioned, and this measures degree of polarization, means how many photons which we receive are polarized, and the angle of polarization, what is the angle of the polarization incoming signal. And this studies helps the scientists to understand orientation and strength of magnetic fields in sources, emission processes in sources, geometry of sources. So, now let us see what is the principle of operation. This instrument is based on anisotropic Thomson scattering of X-ray photons. When the X-ray photons are coming and falling on a scatterer, they will get scattered. Photons from the sources are made to fall on a low atomic mass scatterer. In our case, it is a beryllium. And in this scattering, there is a larger probability of photons to be scattered in a direction perpendicular to the direction of electric field vector of the incoming photon. Here you see azimuthal modulation from polarized sources. If it is a polarized photons coming, then we will see a modulation in the photon count. So, if modulation is not there, then it is a uniform count rate with unpolarized source. So, this is on the rotating platform, there will be 4 detectors which we will see later. So, this is the detector configuration. There are 4 detectors are there in our Polix. So, in here you see there are one detector has been removed so that you can see the inside, and in this detector the top plate has been removed so that you can see the wires here. There are totally 12 wires, they are grouped as 6 plus 6 wires. So, each 6 wires will have the complete processing electronics chain associated with it, and there is a scatterer which scatters the incoming photon, and there is a collimator which restricts the field of view of the instrument to 3 degree by 3 degree. So, this is the complete mechanical configuration. It consists of a scatterer which we have seen in the previous one. So, this is the scatterer, sorry. A scatterer is facing the source. 4 detectors are placed in a cyclic symmetrically to cover all sides of the scattering element. A collimator which will be restricting the field of view. The configuration will be rotated about the weaving axis. So, this is another inside picture, you can see how it is arranged. And these are the few specifications. So, photon collection area is 640 centimeter square, energy range is 8 to 30 keV, and detectors are position sensitive proportional counters, and total weight of the payload is 130 kgs, and the overall dimension of the 4 detectors is 650 by 650 by 600 mm cube. It is excluding the electronics part for the digital signal processing, and total power is about 80 watts. And the data generation rate is 6.5 gigabits per day, and the scattering element used is beryllium, and the lifetime is 5 years for this instrument. So, this is the instrument configuration. You can see the detectors over here. This is 1, 2, 3, 4 detectors, and this is a collimator, and the detectors have the front end electronics right next to them, and there is a processing electronics. They are sitting slightly away from that to process the signals from the 4 detectors. We will see them in details later. So, this is one another complete zoomed in image. You can see the processing the front end electronics sitting here, and the detectors are 4 detectors, collimator, and this is one of the detector removed inside view. So, now how this was constructed we will see. So, this is constructed on the aluminum what you call completely aluminum things which have been machined out. So, they are position sensitive multi-wire proportional counters. 4 such detectors are used to cover all sides of the scatterer. So, this is one of the detector. Here you will see the big bushes here. There are 12 such bushes, and they will be having anode wires. So, and the entire detector is filled with xenon gas at 800 torr. So, this is the wire frame, and this is a zoomed in version of the wire frame. What you see here is each cell has the cathode wires, and in the center there is an anode wire. and in total there are 12 anode wires, 30 anti-anode wires, 350 cathode wires, in total 396 wires have been wired here. So, this is the collimator, so which helps us to restrict the field of view to 3 degree by 3 degree, and there are totally 757 hexagonal tapered holes are made in this aluminum block. And this is the scatterer which scatters the incoming photons when it falls here. So, this is the scatterer which is made of beryllium, and this is been fixed on the aluminum folder. This also is used as the base plate. So, for polarization measurement we need to find the azimuthal distribution of photons falling on the detectors. So, the incoming photon falls on the scatterer, this will get scattered perpendicular to the incoming photon, and while taking one reference direction we can find out which direction they have received in the detectors, because these detectors are rotating and it's rotating on the X-ray, the complete rotating on the satellite, it's on a rotating platform. So, the primary requirement of electronics is to determine the detector and the wire in which the X-ray photon has finally impinged on. So, this complete electronics has been divided into 5 different parts: front end electronics, processing electronics, common electronics, housekeeping and TMTC. So, we will briefly describe this in the next slides. So, this is the complete block diagram of our Polix system. As we have mentioned, there are 4 detectors, and all the 4 detectors have associated front end electronics, because as soon as we receive the X-ray photons, it will get converted into charges, and those charges without any noise related interference, they have to be amplified. Because of that, we have put the front end electronics right behind the detector pockets itself. And once the charges gets converted into voltage, they will be sent to the processing electronics. There we have the analog to digital converters, and further processing takes place in the processing electronics. And there are 4 detectors and there are 4 processing electronic setups are there. So, from all these 4 detectors, the signals needs to be combined, and for that we have one common electronics. So, it will take data from all the 4 detectors, it will combine it and then send it to the satellite bus. Here there is only one system, one common card we have. In case there is any problem with one of the this card, then the entire mission becomes useless. So, for that reason we have a redundancy here. There will be 2 cards here. So, the signals are connected to both the cards, but only one card will be on at a time. If you find any problem, let us say there is one of the card has been failed, we can immediately switch over to the other card and continue with our instrument. And likewise, we have to figure out the health of the system, the health parameters of the entire system also has to be monitored. For that we have housekeeping system. So, housekeeping system will have ADCs for measuring different voltage levels and threshold settings, and it will be sending to a TMTC payload card. From the TMTC payload card, it will be sent to a 1553B card, and then it will go to the satellite bus. Here also there are 2 such cards are used, because if one card fails, the other card will take over. The commands also will be sent through the TMTC cards. So, now let us see how we will be identifying on which of the wire the X-ray photon has fallen. So, this principle is called as charge division. As we were saying, there are 6 wires. Let us say one of the photon has impinged on here, and this will develop the charges. These wires are resistive wires. So, this when it hits over here, this will develop charge. So, here in this place, because the length is lesser, we will receive more charge here, and here the length is more, here we will receive less charge here. So, when we convert this into voltage, this we call it as P1 and this we call it as P2. So, this is for peak 1, here peak 2, because the signal has the photon has fallen here, there are more charge in this, because of that the peak is more here, and this it has to travel for longer distance, this smaller peak here, to know the length from here to here. So, where it has fallen, this is the unknown length, but the total length is known. So, to find out the unknown length, you have to divide this by P2 by P1 plus P2 and multiply by the total length, we will know where the X-ray photon has fallen. So, this is the main principle which is used in this detector. So, this is another zoomed in version, I mean the complete version of the picture. Here are the 4 detectors and the associated the front end electronics are sitting next to, I mean in each of the detector pockets, and the digital electronics things are sitting over here. There are 2 types of cards, one is type 1, other one is type 2. In type 1 we have a common electronics card, in type 2 we have TMTC related cards also, which will help us to take the data from the instrument to the satellite bus. So, now we will see some of the, I mean the history of these cards. So, initially we started with the lab version. So, then the lab version cards were made with the locally available components. So, you can see this is our first version of the front end electronics cards, and these are the first version of the digital electronics cards, where the processing electronics, common electronics and the housekeeping electronics, all cards are been made and we have tested it initially. So, this is the zoomed in version of the individual those cards, and this is how we package and test inside in our labs. So, this is the complete package in the space qualified version. Space qualified version means all the components have to work in the space which goes through the different temperatures, like minus 25 degree to plus 55 degree temperature it has to withstand. All those components were used and this entire system was made. Here you can see there are the back end, the BE packages 1, 2, 3 and another one is the back side, and there are these are the 4 detectors, this is a collimator, everything is a space qualified model has been made, and even the wires also have to be made using the space qualified wires. The complete harness assembly, everything was been made, and this space qualified version was made by a ISRO certified vendor in Bangalore, that is called Centum Electronics, which is in Yelahanka. We did the basic design of everything, and also all testings were done at the lab at RRI. So, these are the different cards which we made for the space qualified version or the final system. This is the front end cards here. So, you can see here this is a high voltage generating card, and this is a high volt HV control card, this is a CSPA card, this is a HV distribution card, this is a power card for this is for the command interface. And the main digital cards were there, P analog card, digital card, then housekeeping card, common electronics, TMTC, payload card, TMTC, RT card. These cards are back end cards, these are front end cards. So, when we go for the space qualified system, we have to go at different steps. One was the lab model, the second model was the qualification model. In the qualification model, all the different temperature and the vibration related things needs to be tested for the system. So, if it is working fine with the different temperatures, then only these systems will be qualified. Here we will use the space qualified components and make the system and check it and make sure that everything is working. Once everything is working, then only we will be making the space qualified FM model or flight model. So, this is in the lab how we have started assembling and testing. So, this is the QM complete test setup here. When we are testing in the lab, we use handle the use the radioactive sources to make sure that the X-ray photons have been detected by the detector. So, this is the again lab test setup. This is for the complete system. You can see there are 4 BE boxes and only one detector. Initially we connected one detector with each of the back end boxes and made sure that everything is working fine. So, this is another view of the entire test setup. So, this is the FM lab tests, and once we do all the lab tests, we have to take this system to ISRO and make sure that all the other tests which are needed to be conducted before it is flown to be done. So, this EMI, EMC, thermovac, and this our system needs to be integrated with the satellite and the test needs to be done, and once this test is done, then we have to make sure that the entire satellite has been assembled and the further tests have to be done. That is called as IST pre-shipment. That means before it moves to Sriharikota. Sriharikota is a spaceport of India. Before it moves from Bangalore, we have to test the entire thing here. That is why it is called as integrated satellite pre-shipment test. Once this is working, then we are ready for launching the system. And during all this test, data from the Polix was verified and found to be fine. Because if you miss anything, once a satellite is launched, you cannot go up and fix the system. So, make sure that all tests are done, everything is working fine. So, this is some of the tests which we did at ISRO. This is the thermovac chamber. So, all 4 detectors and our back end boxes, everything has been being put into the thermovac chamber, and all the tests were done over here. So, this is one of the another view, another zoomed in view of the same chamber. So, this is connection being done and tests are going on. So, this is again some more tests were done. At that time a photo was taken. This is for the vibration test. So, this is EMI EMC test being done at ISRO, and this is a complete system. So, all 4 backends and 4 detectors are here, and this has to be, as we are mentioning, this has to be integrated with the satellite. This is a solar panel. This is our Polix being integrated on the satellite bus. You can see this is a complete satellite bus, and this is the Polix. So, this is the ExpoSat configuration. These are the solar panels. This is the Polix. This is the backend electronics, and this is the X-ray spectrometer from ISRO. So, this launch took place on 1st January 2024 at Sriharikota, and the orbit is low Earth orbit. Altitude is about 650 kilometer, and inclination is 6 degree. And orbital period is 97.7 minutes, number of orbits per day is 14.7. So, that is all.